And welcome to part 2 of our ellipse video. I'm going to go back and start with the idea of a cone. And again, from the past, we saw that when we're making a cut in the cone that's kind of parallel to the slope of the cone or the side of the cone, making that kind of parallel cut, we get the first conic section, which is the parabola. This shape right here is a parabola. And that kind of corresponds with we say an eccentricity of 1 to 1, we get a parabola. And that it kind of equates to the idea of you're kind of cutting sort of in the same direction or parallel to the cone. And now we're going to look at what happens when eccentricity is less than 1. And we're going to find out that has to do with, instead of kind of cutting the cone, see if I can orient this properly. Instead of cutting the cone kind of parallel, okay, to the side, making a parallel cut, I kind of lower the angle down, make a little bit of a flatter angle cut. And when I make that flatter angle cut, again, here's kind of this side, so I kind of lower the angle and make a cut through the cone in this fashion, I end up getting the ellipse shape. So, and that's going to correspond to the idea of eccentricity less than 1. Now, we're looking at eccentricity a little differently than sort of cutting angle. But in a couple days, you'll find out that cutting angle and this idea of point to focus, point to directrix actually are related. But that's for later on. So what I'm starting off with here is the idea of, let's say we have eccentricity, which remember is point to focus over point to directrix, no longer in a 1 to 1 ratio, but in a ratio that's less than 1 to 1. And let's see if I still have it here. You might remember the other day in class we did one with an eccentricity of 1 to 2, and we kind of made this, this elliptical shape. So we're going to look at one more example and hopefully show you that this also turns out to be an ellipse. So eccentricity of 2 to 3. Let me fill this in here. When we're under 1, we end up getting the ellipse. And then, of course, later on we'll get into what happens when that eccentricity is over 1. You might be able to guess at this moment right here. So, okay, so here I have a, let's move that over a little bit. I have a directrix right here, okay, get that out of the way, and I have a focal point right here. And so my focal point happens to be 5 units away from the directrix. And I'm going to try and find points that satisfy a 2 to 3 eccentricity ratio. In other words, for every 2 points I'm away from the focus, I'm 3 points away from the directrix. So really anything that comes into a 2 to 3, 4 to 6, 6 to 9, and so on. Really, that's what I'm looking for, anything that comes in a 2 to 3 ratio. So as we did in class, we'll try to just find a few by kind of casual inspection. Can I find any kind of point between F and D that fits a 2 to 3 ratio? Well, I've made it kind of easy on us where I've kind of created 5 spaces. So then this spot right here is 2 spaces away from the focus, and it happens to be 3 units above the directrix, and that's a 2 to 3 ratio. And so now we're going to look for a few other points that satisfy a 2 to 3 ratio. When we did this the other day, we were able to get some points that were kind of across from the first focus. And that was pretty easy to do. This one's a little more challenging. There's a spot over here somewhere. Let's kind of check a few. This spot right here, this would be 3 to 5. And so 3 to 5, unfortunately, that's not a 2 to 3 ratio. If I go out a little further, that's going to be 4 to 5. And once again, that's really not a 2 to 3 ratio. Further out I go, I'm kind of getting further and further away from a 2 to 3 ratio. So I probably need to come in a little bit somewhere to get myself a nice 2 to 3 ratio. Well, let's think a little bit about this, about what would this have to be? So in other words, I don't know what this is, so let me just call that x. But wherever this spot happens to be, I know that this is 5. That's certainly that it's a 5. And I want this to be, work out to be a 2 to 3 ratio. So if I do a little cross multiplying, 3x equals 10, divide by 3, x would be 3 and 3 1/3, telling me that if I go from the focal point out 3 1/3, 1, 2, 3, I'll do it in pencil here for just a second to make sure I didn't make a mistake here. 3 1/3 versus 5 seems to be a 2 to 3 ratio. Now let's go ahead and check that. If we do 3 1/3, now 3 1/3 is 10 thirds, so 10 thirds, and if I divide that by 5, it does make a 2 to 3 ratio of 0.666, so on. So 3 1/3 works out very well. So I'll go 3 1/3 to the right, and I'll go 1, 2, 3 1/3 to the left, and so there are a couple of points that work out. So let's now find some other points, and once again I've kind of got my little paper ruler here to kind of help me measure along different angles, and I'm looking for things that make a 2 to 3 ratio. So let me get this out of the way for right now, and let's think about other combinations, easy combinations that make a 2 to 3 relationship. So another one could be 4 to 6. Can I get something that's 4 away from the focus and 6 above the directrix? So let's start with the directrix. Up 1, up 2, 3, 4, up 5. So here we are. Here's what I often call the 6th level. This is where you're definitely going to be 6 above the directrix. Somewhere along this line, I will be exactly 4 units away from F. And so I'm just going to do it by measuring. So it looks like from F, if I go out 4 units, 1, 2, 3, 4, right about here, right about there, 4 units, maybe right around there is my guess, would be a point that's 4 units away and 6 above. Now, some of you might be able to actually calculate this. You might see the right triangle here of 1 squared plus x squared equals 4 squared. So if you did kind of 4 squared minus 1 squared, you could actually calculate how far over to go with this point. Okay, and that would probably be a bit more precise. But I'm just going to kind of do the measuring way just to kind of hopefully save us a little bit of time. And by the way, if after watching a few of these, if you kind of see where I'm going with this, feel free to skip ahead in the video as these points evolve. So I found 4 to 6. Let's now go for something else that's in a 2 to 3 ratio. So aside from 4 to 6, what else? I guess I could have, let's see, add on another 2 and add on another 3. I could go for 6 and 9. It's like I want to be 6 away from the focus, and I want to be 9 away from the directrix. So let's see. 1, 2, 3, 4, 5, 6. I guess I should erase that line. That's the 6th level. 7th level, 8th level. So here's the 9th level. Here's the 9th level right about there. And I want to be 6 units away from the focus. So if I try to again get myself 6 units from the focus, so let's see, that'd be 1, 2, 3, 4, 5, 6 is right about there. So maybe, again, right around there would be the, that would be 6 away from the focus. And it's 3, 6, 9 above the directrix. So there's another point. And so then I could go 6 units in this other direction, or I can just kind of take a mirror image. Let's see, 3, 6. So right about there, okay, would be another point. And you can kind of see how it's starting to kind come back around to kind of complete the ellipse. So the top is probably going to be up here somewhere. But let's go ahead and try a few more points, and maybe we can just kind of walk right into it. So if I double again, let's see, add on 2, that would be 8, add on 3, 12. And so I look for something that's like maybe an 8 to 12 relationship. And so, okay, so I'll look for the 12th level. This was the 9th, 10th, 11th. So here's the 12th level. Everything here is exactly 12 units above the directrix. So now I'll try to measure and get 8 units away from the focal point. And let's see, 1, 2, 3, 4, 5, 6, 7. Ooh, boy, I almost got it right on the dot there. So let's see, that would be 1, 2, 3, 4, 5, 6, 7. So 8 away. So okay, kind of maybe right around there. Okay, that would be 8 away from focus, 12 above directrix. And let's see if I can do that again. 1, 2, 3, 4, 5, 6, 7. Oh, got to bump him out a little bit. So again, it's the only problem with this method is it's not the most accurate. Just trying to conceptually give you an idea of what these distances look like. 1, 2, 3, 4, 5, 6, 7. So it's only more like that, maybe right there. And again, if we wanted to be more precise, I guess we could do, let's see, this would be 7 squared, and this would be 8 squared. So if I did 8 squared minus 7 squared, I could calculate what distance would really go there. In fact, let's see if I can do that real quick. 8 squared minus 7 squared is about 15. So the root of 15 is about 3.8. So it probably should be just a little short of 4 marks over. So 1, 2, 3, maybe a little further out right there. Okay, so those are the 2 points there. So we got 8 to 12. And then let's double again, go 10 and then add on a 3. So we'll go for 10 to 15. Now the 15th level, 12th, 13, 14. So here we are at the 15th level. And I need to see if I can get 10 away from the focus. Now again, I'm not sure if I have enough ruler to do this, but we'll try. Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9. Ooh, not making it. I gotta, maybe I can squeeze them out. Oh, you know what? This is 1, 2, 3, 4, 5, 6, 7, 8, 9. It's 10 straight up. Okay, so that's, we've kind of stumbled into the very last point of the ellipse right in here. So the ellipse, again, kind of roundish. Okay. We'll just kind of try to keep bringing them around like so. Again, it's a very kind of rough sketch of the ellipse. And all the points along here will satisfy that 2 to 3 ratio. Point to focus, point to directrix, that eccentricity ratio. This one ended up being a lot bigger than the one we had done previously in class. And so I'm not sure why that is. If it has to do with the spacing, this is only 3. The gap here was only 3. The gap here was 5. Or it may have something to do with the fraction, 1/2. I mean, 2/3 is a bigger fraction than 1/2. So I'll leave that for you to kind of think about. But here we have the ellipse. And now we're going to add a few more things to this diagram. So let me kind of get rid of some of these sort of extra lines. I really don't need them anymore, and they might kind of confuse folks. All right. So let's see what we can come up with here. So we have this line right here, which is a directrix. Well, it turns out there's another directrix, right on the opposite side. So let me go up to the top here. 3 above the top. This would be another directrix. And so what we say is you actually have a pair of directrices. Okay, let me zoom back a little bit. Okay. And so this, we can maybe call this D1 and call this D2 for directrix 1 and directrix 2. And there's also another focal point right here. So maybe we can call this focus 1 and we'll call this focus 2. So again, you have directrices. You have what we call foci, right? Two focuses we call foci. That's spelled F-O-C-I. Okay, that's the sort of the plural. So directrices, foci, and then some other important parts of the shape would be, let's see, right here. Well, there's the center right between the two focal points. I guess right there would be the center of our ellipse. And then, of course, these points right here, for a parabola, we call this like a vertex, and so this is also a vertex, but there's another one here as well, and we call these vertices. So I'll call that vertex number 1 and vertex number 2. And so you have a lot of things going on with the ellipse. You have directrices, you have foci or focal points, you have vertices, and then you have the center. These points out here we actually don't call vertices. They have a different name which escapes me right now, but we'll hopefully get to those a bit later on. And so now you've kind of got the layout to kind of see where things are in relation to each other. Now I'll add a little more terminology to this here. So let me kind of get these out of the way. All of our scratch work, and let me take foci out of there. Okay, this segment that goes from vertex to vertex, from here, vertex to vertex, okay? We call that the major axis, okay? That's called the major axis. Okay? It's the biggest of all the diameters in the ellipse. And then we have one that's going across, okay, which is the shortest of all the diameters. That one we refer to as the minor axis. So you have the major axis, which is the longer of the two, and the minor axis, which is the shorter of the two. You will always find that the major axis, on the major axis, that's where the focal points and the vertices lie. So these things will never lie on the minor axis. They'll always lie on the major axis of the ellipse. Okay? So we have the major axis, we have the minor axis, focal points, we have center, vertices. So all this terminology right here that you'll hopefully get pretty comfortable with, pretty soon. But there's one other thing to share with you in this diagram. And I'm also going to use the diagram we made from our last class. And some very interesting measurements come up. Okay? If you measure from center to focus versus center to vertex, so center to focus, center to vertex. Okay? In this case, from the center point to the focal point is 4 units. And from the center point to the vertex is 6 units. That reduces to a 2-to-3 ratio. In other words, it matches the eccentricity ratio of the ellipse. Now you're wondering, maybe that's just for this ellipse? Well, if we take the one we made the other day, where here we had eccentricity of 1/2, and if you go from the center to the focus, that was 1, and the center to the vertex, that was 2. So once again, it matched the eccentricity ratio. So center to focus, center to vertex, it turns out for every ellipse, okay, that will be the same proportion, okay, as the eccentricity proportion. That ends up being a pretty useful little idea. Okay? So let me give you another ratio. This one involving the directrix. If you go from the center to the vertex, in this case center to the vertex, that would be 1, 2, 3, 4, 5, 6. And then if you go from the center to the directrix, that would be 6, 7, 8, 9. So center to the directrix. And if you reduce 6 over 9, why, that reduces to a 2 to 3 ratio as well. And if we go over to this one and we check it out for this one, let's see, from center to vertex was 2, from center to directrix was 4. 2 to 4, that's a 1/2 ratio. And so here's another ratio that happens to match the eccentricity ratio. And these will be very useful to you when you're asked to draw an ellipse and kind of locate all the pieces, the focal points and the directrices and the eccentricity. You'll find that these ratios are pretty useful in doing that. I guess I could give you a whole bunch of different formulas, but that to me just seems a waste of time, too much stuff to have to memorize. It's probably more useful to kind of understand these relationships. And as you draw more and more ellipses, you can kind of test these different ratios to see if they match the eccentricity ratio. You will be pleasantly surprised. And so now we have a lot of good information about focal points and directrices and eccentricity that we're going to be able to apply to the problem on video number 1. However, there's one more video you have to watch, which it's not a video that I made, but one that I found on YouTube. So if you can now move on to video number 3, and then once you're done with that, we'll be able to kind of go back and look at our original problem. So thanks again.